So, good morning, everyone, and welcome to ADC, and welcome to the Complicated Plugins workshop we're looking at on this morning. Just to, I guess a few introductions. So my name's Ross. I'm the head of embedded software at Focusrite. So I look after all of the firmware, audio, automation, PSP teams. Joel this morning is going to be the main man and taking you through, taking you through the workshop. So he is a senior DSP developer on our DSP team at Focusrite, and spends all this time thinking about DSP. And then we've also got James Hallowell, who's one of our lead developers on our DSP tooling teams. So for those of you that haven't heard of Focusrite, just a brief introduction to us, we are a music and audio tech group. We have 13 brands making various products all across the audio and the music industry. Why this workshop? So this is, we wanted to share with you some of our kind of development process, the way that we kind of approach this stuff is similar to what we would be doing as we go through the development process. So we kind of want to take you that. Hopefully you'll take away some knowledge, you'll take away some cool tips and tricks for how we think about it. So, without further ado, I will hand over to Joel, who will take you through the first part of the workshop.
After I'd been studying with him for 2 years, Schoenberg said, "In order to write music, you must have a feeling for harmony." I explained to him that I had no feeling for harmony. He then said that I would always encounter an obstacle, that it would be as though I had came to a wall through which I would not pass. I said, "In that case, I will devote my life to beating my head against that wall." Good morning, everyone. How are we doing? So I'm Joel. I work on embedded DSP at Focusrite, and today I want to talk a little bit about filters. So a little outline of the workshop. So we're going to talk a little bit, a little history about this paper that we're going to be talking about today. And then we're going to have a look at the paper. Then we're going to get started a little bit with Jupyter Notebook and play around with it. And we got a little bit of an experiment in Reaper, after which we start building a filter step by step and kind of understanding what it's doing at each step. Then we're going to implement the paper filter before porting that to C++, testing it, and then bringing it into a JUCE plugin. So that's a lot of stuff, but hopefully we're going to have some fun with it. So just have a little bit of a demo of the plugin that we've got for you. So what we've got here, the filter is being impulsed, it's being excited by a sound, and we've got a bank of these filters with controls for the gain and the decay of the filter. And if we just play with these a little bit, we can get some kind of interesting sounds out of this, and kind of pick out a harmonic, maybe change its decay so we have slightly more of a short sound. Maybe pick out a particular harmonic to ring. And so the plugin that uses the filter that's in the paper that we're going to talk about today. So back to that. So there's a repository. I hope everyone got the link. If they didn't, it's at the bottom of this slide. Paper 2 plugin ADC 25 on GitHub. Inside that repository, there's quite a lot of stuff. I'd show you. So we've got some notebooks, which we're going to use. So you should have found already this Getting Started notebook. So if you're looking on GitHub, you can kind of have a look at them and see them in place. This is one of the nice things about Jupyter Notebook, that you can easily see, and the results are included there. Then there's quite a few other notebooks that we're going to get to. So the first thing you're going to want to do before we go on is check out the workshop branch in the repo, which has everything that we're going to be looking at today. So also in the repo, there is there's some markdown files. There's this solutions MD, which contains kind of answers or completed versions of the code that we're going to be going through. There's resources, which contains a link to the paper at the top in different formats, so you can go and pick that up, as well as lots of other resources that might be interesting. And finally, there's this toys HTML. Now, if you download that, or you've cloned the repo and you open that in your browser, you'll get a page that looks like this, which has a lot of interactive figures on it, which we're going to be looking at today. So a little history. The paper that we're looking at today was a collaboration between Max Matthews and Julius Smith, which resulted in a program that could filter sound with many efficient notches. The frequency and amplitude of these could be independently controlled in real time with MIDI controllers like the radio baton that's pictured. And this is an invention of Max Matthews that's used a bit like a cross between a Wii remote and an electric drum pad. It didn't really catch on, but it looks fun. So a little about these two characters. Max Matthews was really the first person to think of using computers to make sound. So all the way back in the 1950s, he was using big mainframe computers controlled by punch cards. He had a system called Music N, which was an environment where you could kind of chain together different, what he called opcodes, which processed or generated sound. And this was like an inspiration for much of the kind of music programming systems that came after. And I guess since now all music is really computer music, everything that we do today, we owe a great debt to Max Matthews. His name lives on in Max of Max MSP. And he even inspired the scene in 2001: A Space Odyssey, where Hal is singing. They had a version of that produced by a computer all the way back in the early 1960s. And Julius Smith worked with John Chowning, was responsible for the FM synthesis in the DX7. He went on to work with Yamaha on the waveguide synthesis in the VL1 synthesizer and contributed to the design of Shazam. So, the paper. So Max Matthews said about this, he called these filters phaser filters, which is a slightly snappier title than the long description given in the title of the paper. He said of them, the main perceived effect of filtering a sound with a bank of phaser filters is to change the timbres of the file. The effect is much stronger than I expected. Filters cannot add new frequencies to the output sound. All the output frequencies must be present in the input. But the strength of the input component can be greatly changed, and the duration of the component is greatly increased by filters with long decay times. Perceptually, the filtering seems to throw away the input wave timbres and create highly resonant sounds. The resonant frequencies and decay times coming from the phaser filters, often the perceived timbres, are interesting and sometimes very beautiful. So the title of the paper, the first thing we'll look at, requires a little bit of unpacking. So it says methods for synthesizing. So there's two elements here. You can use these filters to generate tones. You can also use them to process an input file. So when he's talking about synthesizing, you might be actually literally talking about synthesizing. Then very high Q. So This means that they're really narrow. They basically produce single frequencies rather than like a band pass filter, which might pass through a range of frequencies. They really only operate on a super narrow frequency. And then they are parametrically well behaved. This means basically, unlike some filter designs, you can change the frequency, you can change the decay time as much as you like, basically, and they really behave well. That's in contrast to these other filters where you might see some kind of discontinuity, like the gain will change in an unexpected way when you modulate the frequency of the filter. So I'm just going to quickly go through the rest of the paper just to show you what it looks like. So there's a lot of mathematics here. It looks maybe a little bit intimidating at first sight. There's some matrix equations here. There's an awful lot going on, but don't panic. All we actually need is these three little bits here. So there's this equations 12 and 13. These really, if you write this in code, it looks almost exactly the same as what's here in 12 and 13. And then there's a couple of definitions for how you produce the coefficients. That's the little values just to the left of the filter values there. So then there's a few parameters that this gets. There's the decay time, there's the frequency, and there's the sample rate. I've just included here that the decay time is specified as this tau, which is 1/e, and that's actually the RC time constant. That's the time it takes to charge a capacitor, which comes up quite a lot in DSP, this 1/e value. If you're doing something like working on compressors and dynamics processing, often you're using this value, this tau, which comes all the way back from the electrical engineering of how long it takes to charge a capacitor. So, getting to Jupyter Notebook. First thing we're going to do is make a sine wave in Jupyter Notebook. So there's a few steps to get started with the Jupyter Notebook. So hopefully, if you've followed the instructions that were in the repo, then you'll have installed a virtual environment. And the first thing you'll need to do is to activate the virtual environment and then run Jupyter Notebook. So if I just so to do that, the instructions are in the repository for macOS and for Windows separately. It's a slightly different thing. So you'll want to take the activate line that's here in the instructions. So I'm just going to take that for the macOS version, and so you'll want to be in. A quick reminder: if you have to check out the workshop branch, if you haven't already done that. Then so you'll want to cd change the directory into the notebooks directory and activate the virtual environment. And then you can start Jupyter Notebook, which you can, I'm going to use this one. Run just typing Jupyter Notebook. And if you're on Windows, you might want to select no browser, because there could be an issue there, and then take the URL that's output there and put that into your browser. So now at this point, you'll be presented with this Jupyter Notebook environment. You're in the file browser. And if you want to open a notebook or create a new one, you can create a new notebook by selecting File, New Notebook. But I'm just going to go and open the Getting Started notebook. So in this environment, when you've got this open, it's broken down into different cells, these little code blocks here that you can select by clicking on. And once you've selected one, you can press the little play button up here, which will run it. Alternatively, if you select the Run drop-down menu, you can choose to select only run only the selected cell, or you can choose to run it and go on to the next one. The keyboard shortcut will be there for whatever platform you're on. So I'm going to continue by using keyboard shortcut to run the particular cell and not go on to the next one. So I'm going to run that one. So this is going to import the NumPy and the matplotlib libraries so that we can work with some vectors and plot the results. While that's running, there's a little status up in the top right-hand corner. While it was running, this is a little gray circle, so you can see whether it's still going. It doesn't give you any other indication. When it's finished, it'll return to white, and then it'll be done. So continuing to work through this. So we're using the NumPy library. NumPy works with arrays. It allows you to manipulate them in very sophisticated ways, often with very, very little code. So the easiest way to create an array is to choose a size of your array and then use the zeros function, which is going to generate an array of that length, which is all zeros. So if I go do that, I'll now have this array of all zeros of length 10 referred to by the variable signal. And I can also plot that. So we have only to write plot and the vector that we want to plot. Then it's nice to have the grid so that you can see where values line up. And you may need show, but often you can get away without that. So if I run that one, it'll show me the same figure that I've already got. It's all zeros, which is what we expected. But you might also want different vectors that aren't all zeros. One you can do is all ones, which is just the function ones. So if I change that to ones very quickly, I'll see everything is one. There's also this A range function, which takes the starting value and one past the finishing value. So that's going to have generated a vector of 1, 2, 3, up to 15. And it's referred to by A. And then we can also do all kinds of operations on that just using basic arithmetic, and that's going to operate on every single element independently. So here we've divided every element by 16. We've squared every element. We've added 1 to them, and then we plotted the result, and it produces this nice little growing curve. I run that again. Oops. So I think that covers that. So we're going to draw a sine wave. We need 3 things to draw a sine wave. We need a sample rate, we need a frequency, and we need a duration. So we just specify those 3 parameters. Then we need to know how many samples that we're going to have in our sine wave. So to do that, we multiply the sample rate by the duration. That's because the sample rate is the number of samples per second. So if we multiply that by a number of seconds, so duration is specified in seconds, we get a number of samples. So a little note about phase. So we're going to want to progress through a sine wave at a particular rate. I've simplified here by saying I've got a sample rate of 10 samples per second. It's very low, but it's very easy to think about. So if we want to get from 0 phase, that's the beginning of the sine wave, to the end of the sine wave, which I've said is 1, we'll want to do that in 10 steps. So that means each of our steps is 0.1. So we've divided our frequency in cycles per second, the number of times that we're going to go through that phase in every second, by our sample rate. And we get this little increment, 0.1. And every step we increment by our phase increment until we get to 1. And then we can see this here again, the phase increment. It samples the sine wave, which is like a continuous function, but we've sampled it, and we've sampled it at this phase increment. If you had a much higher sample rate, you'd see a lot more steps in between these ones. But also, if you had a much lower frequency, you would have many more points again. So we've got this kind of dual. You can increase the sample rate or decrease the frequency. It has the same effect on the resulting output sampled waveform. That's showing that the representation is subjective. It means you have to decide what the sample rate is before it has any meaning. So here we have this phase increment, the frequency divided by the sample rate, and we're going to iterate over the number of samples and fill in our signal vector with cosine wave. It's all scaled by 2 pi because that's the scaling of a mathematical sine wave. We might normally say it's from any number, like 0 to 1, just for convenience, and then just scale it at the end. So in the end, we've got 2 pi multiplied by this phase increment and multiplied by the index. That takes us to the number of samples that we want. So we go back to the notebook. So if you create a new cell, or just select the new cell at the end, in the repository, in the solutions file, everything's completed here. So you can just take this solution here and paste it into the notebook. And when you run that, you'll get a sine wave plotted if everything's working. So a couple of things to do here. So at the moment, we've got a sample rate of 48 kilohertz. If you want to just play around, choose different frequencies and sample rates, you can kind of see how it affects what we get in the plot. So what I'm going to do is I'm going to say we've got a sample rate of 1 kilohertz, and I'm going to give us a frequency of 0. And this produces this result of all ones. I reduce the duration a lot to 0.1. And I've just changed the plot. This is another nice way of plotting things. It's called STEM. And what it's going to do is it's going to produce lots of these little lollipop figures, each one for each sample. Let's reduce the length of this again. So this is a very important signal. This is 0 hertz, or we call it the DC frequency. Again, a term from electrical engineering. So at this frequency, we're just staying in the same place. We're not moving. If I now increase this all the way to 500, we can see we're doing almost the opposite. Instead of staying in the place, we're going as far as we can. We're going from 1 to -1, back to 1, down to -1. This is a special signal. It's called the Nyquist frequency, and it's the highest frequency that we can represent in any sample rate. It always looks like this, whatever the sample rate is. So if I now change this to 8,000 and I change this to 4,000, it's half the sample rate, we're going to get the same signal, but more samples. It's oscillating or swapping +1, -1, +1, -1. And we'll see this again and again. So if you go to the interactive figures, we have a figure that shows this in a slightly nicer way. So in this figure, frequency is going, it's written down the bottom, from 0 to 1, where 1 is at the sample rate and 0 is at 0. And as you see, as we increase the frequency and we're sampling this continuous waveform, when we get to that halfway point and we have that +1, -1 figure, if we continue, you can't represent what's happening in between these samples. It's kind of too much going on to represent with that many samples. This is aliasing. So what you get is that we start seeing the same patterns that we saw before we got there. So at 0 frequency, we see ones, all ones. If we go all the way to the sample rate, we still see all ones, but we can't represent this waveform. And actually that reflected pattern, so there's like a mirror image around the 0.5 mark, happens for all of the intermediate sample intermediate frequencies. So at 0.75, we see 1, 0, -1, 0, and that's what we would have seen here, but this looks like a much more sensible sine wave. What we're seeing is that we can't represent that, and it just reflects or folds back and starts looking like a totally different frequency than the one we're actually trying to sample. So this is the aliasing effect of sampling. So that highest frequency is called the Nyquist frequency. I've shown an intuition as to why we say that you can't sample above this Nyquist frequency without getting aliasing. And these two important signals, the DC signal and the Nyquist signal, which I'm going to refer to again and again. So a little bit about frequency decomposition. So it's common to think of breaking down a sound into harmonics, harmonics in the harmonic series. So if you play a note on a piano, you'll have different tones in the sound. So you'll have one octave above, an octave and a fifth, 2 octaves, two octaves and a third. These are the harmonics of the sound, but we can actually extend that idea so that we have a continuous range of frequency that extends from 0 to the note up to infinity. And this useful idea, I kind of think of it like having this nice microscope that you can look at a specific frequency and think about exactly what's happening there and only there. And we break that down into sine waves or sinusoids. So you can kind of think about what's happening in a sound as this infinite sum or kind of infinitely many contributions of infinitely narrow single frequency sine waves. So we're going to go on to building a filter. And the first question I have is, what is a filter anyway? So when we talk about filters in general, we kind of mean anything that takes some kind of input, does something with it, and produces an output. So it's modified a signal. Your guitar amp is a filter. the cabinet itself is a filter. Every pedal in your guitar rack is a filter. But, well, even like as on this slide, you see the Millennium Bridge. It's got physical dampers under the bridge to stop it from vibrating too much. These are filters, just physical filters for physical vibration. But when we talk about digital filters, we sometimes mean something slightly narrower. So that means we're talking about what are called linear time invariant filters. Just to unpack that, it's a formal definition of a filter. It has these two constraints, which if we keep these two constraints, we get a number of powerful tools that we can use to analyze the behavior of our filters. The first constraint of the linear time invariant filter is linearity. This means that we can consider the effect of the filter on every single frequency independently. This is like the microscope that I was just talking about. You can look at all of the frequencies independently and believe like it's as many filters as there are frequencies that are all acting separately on each individual frequency, and then they're all put together at the end, and you get back what you started with. The second constraint is time invariance. That means nothing changes about the filter. You specify it, and you decide on the input signal to that filter, and then you never change anything. They're just static. And if we don't stray too far away from that time invariance, we can still make use of a lot of the tools that we get by using this LTI filter theory. So some examples of things that don't fall into the category of these LTI filters, which are not linear. Things like distortions or modulation effects, so phasers, flanges, these are not linear, they're not LTI filters, they're not what are covered by this theory. So in the end, an LTI filter, it's only able to affect two things. It affects the amplitude of each of the contributing frequencies, and it affects the phase of each of these contributing frequencies. So we're going to do a little bit of an experiment. So this is going to involve Reaper. So the experiment is this patching diagram. If you're comfortable using Max MSP or Pure Data or any other environment, you can set this up. If you happen to have some lab equipment and a tone generator and a delay and a mixer, then you can do that as well. But this block diagram going to produce in Reaper using built-in plugins in Reaper. We've got an oscillator, we've got a delay, and we mix these two signals together and we see what the amplitude is at the end. So if I open Reaper, so if you want to follow along, the instructions are to open Reaper and turn the output bus down to as low as it goes. So we're not making sounds in the room. Create a new track and add the tone generator plugin, should be included with Reaper. And after that, add someone's making a sound, rear delay plugin after the tone generator, and the VU meter after the redelay plugin. Then you go to the redelay and you set the wet-dry mix to 100%. What I mean by that is in the delay, these two sliders should be in the same place, both at 0. Then you want to set the length of this musical delay slider all the way down to 0. And on this one, choose the little entry box and type in 0.02 and press enter. That might go away at some point and it'll just say 0, but in my testing it's always still set, whether it now says 0 or not. Now that we've done that, if you go to the tone generator, you can set the dry mix to 0 and the wet mix to, the dry mix all the way down, negative 120, and the wet mix to 0. And then you set the frequency to 0. And you should see, you might need to double click on the, where it says VU meter at the bottom. If you double click on that, it should spin it out as a separate window. At this point, if you slowly increase the frequency on this slider on the tone generator, you see the gain on the VU meter goes all the way down. It says minus 20, but that's just as far as the meter goes. It's gone to 0. There's no signal. And as we go back down again, our signal comes back again. And if we go to rear delay again, and instead of 0.02, we select 0.04, and we try the same thing again. We increase the frequency slowly, but this time it goes all the way down halfway before coming back up again. So our dead spot, as it were, is in the middle instead of at the end. If we continue the same pattern, so say 0.06 here, you'll see there's a drop here. This is about a third of the way through, and then it comes all the way back before going back down at the top. If you're not seeing this same effect with the numbers that I plugged in, try changing your sample rate to 48 kilohertz. The delay times that I'm using are calibrated to 48 kilohertz. So you can do that by choosing the audio device settings and selecting the sample rate you want. So the question is, why are we seeing this effect? What's actually happening that means that when we change this delay and add the signals together, we're seeing drops that appear in different places in frequency as we sweep with the tone generator. So to see an answer to why that's happening, if you go to the interactive figures, the first effect that is causing that is what happens when you add two sine waves together with some phase offset. So when I move this slider across here, it's changing the phase offset, and it's changing it between no offset and all the way back round so that it's realigned a whole cycle. And you see at the halfway point, as we shift the two sine waves across each other, we've aligned it so that at every point in time, we're adding, say, 1 to negative 1, 0, adding negative 1 to 1, 0, and every point in between, they balance out so that the result is 0. And this effect smoothly comes into play and then goes away again as you cross these. But the next thing that's going on here, so I should say, okay, in this figure, the time offset is the number of samples. You can select partial number of samples. So you have to imagine this is like a continuous wave. We've done this and recorded the result. It just happens that these line up at particular samples when we shift it slightly in time. So if I set one sample time offset here, and then I sweep the frequency, and you see the gain of the output. So what we're seeing here is we've got, again, two input signals and an output. And we add these two together. just like we saw in Reaper, these have cancelled out completely. And it's really clear here because we've got this Nyquist signal. Remember, at half the sample rate, you get the signal that oscillates between +1, -1, +1, and -1. And if I just shift those across by one sample, then you're adding the sample where it's +1 to the sample one delayed where it's -1 every time. And that just cancels out completely. Similarly, if we select a delay of 2 samples, you can see that when we do that and have the same shift at half the Nyquist frequency, so now we have a sample in between. So we go 1, 0, -1, 0. But now with this offset, we're again adding 1 to -1 because the frequency has changed. So what we're seeing is that a particular delay has a different effect at different frequencies because the length of the wave, the time it takes to complete the sine wave, has changed. And as we increase the time offset, it puts the point at which these two waves will synchronize in this opposite fashion at a different frequency. And below that, you can see how this looks in frequency. So this graph shows positive frequency, and it's slightly different from the ones that we've seen before because it goes to pi, and it also goes to -pi. This is, again, just zero frequency in the middle, the Nyquist frequency here, but the rest of the sample rate kind of goes somewhere. We call it negative frequency. It appears on the left-hand side of this axis. And as I increase this slider to one sample, you see how the gain has changed over frequency. It's exactly the same effect that we were seeing here. If I set this to one sample, you see the same slope in the gain of this output on the seconds, on the output plot, that it goes down to 0 at the Nyquist signal, Nyquist frequency. And as I increase this, we see how that effect changes the result. We get this, and it will increase endlessly. This thing just squashes in as we increase the time offset. So you get more and more and more of these little dips. And one reason for showing this on this particular axis is that there are exactly the same number of spaces between the dips as the sample offset. So if you've got a sample offset of 8, a delay of 8 samples, then you have 8 spaces between the dips. If I set it to 5, which is an odd number, it's clearer because the last one isn't split. 5 spaces between these. And that will always hold. But if you think about having a very long delay, this is where the LTI filter theory comes in. If I have a delay of a very short sound for a very long time, there's no opportunity for those to add to each other in such a way that they're going to cause these dips. So it's the theory is kind of imagining that you've just got these constant waveforms that are just continuing forever. It's only true in the real world in a very small snapshot of time. So back to building our filter. Basically, what we've seen is we've built a filter already. We've built a very simple filter, which just cancels out frequencies at these equally spaced locations. And all of the filters that we're going to make basically behave the same way. We add signals together, we delay signals, and we also scale signals. So we've got some control over the amplitude with multiplication. So the first well, the block diagram is the tool that allows us to kind of build filters by connecting these blocks together, connecting these basic building blocks together. We can always have an input. We progress from left to right, going from the input to the output and following the arrows. There's little arrows on the figure. So what we have here, we add a delayed version of the output signal. There's a little black dot, that's a kind of a tap. So the signal that continues around here is the same as the one that continues here, that it gets tapped off with this black dot. So we're going to come in and then delay our signal, multiply it by a value, which is negative A1. That's just a name for the value we're going to multiply it by, and then add it back to the input and continue around like this. That's how to read the block diagram. Then we have a few more tools for understanding our filters. We have the difference equation, which allows us to produce this impulse response. We have the transfer function, and we have the frequency response. And I'll explain all of these as we go through building these filters step by step. So the first filter that we're going to look at does nothing. It takes us from the input to the output. It sets our output to the same as our input. So in the difference equation, which is essentially how we're going to build a filter, the code is going to look a lot like the difference equation. The difference equation describes how we get the next sample from a combination of the previous input and output samples. In the notation, we use this little sub n to describe which sample in time we have. So n is our current sample. So yn here is our current output sample. xn is our current input sample. And if we wanted to describe past samples, we'd use like a little n minus 1. Or if you want even further in the past, you'd have n minus some larger value. We also have this transfer function. So the transfer function, it's a function of this little value z. Z is essentially, it's a frequency. It tells us which frequency on the microscope we're looking at. So if we're looking at the filter just at the frequency described by z, exactly what kind of value z can take, we'll get to a bit later. But for now, z is basically, it's a frequency. So the transfer function is a fraction that takes our input and our output. So it divides our output by input like this. So x of z was our input in this microscope view of the filter, just looking at that frequency, and y of z is our output. And our transfer function, because we had a filter which it doesn't do anything to the signal. So yn and xn are the same. So any fraction where the top and the bottom are the same is 1. So our transfer function is just 1. So we use the transfer function to basically pull out the behavior of the filter. So it's not described kind of implicitly in terms of the input and the output. It's just the filter. And we can use it to do quite a lot of useful things. So with the transfer function, we can compute the frequency response. We can calculate what are called poles and zeros of a filter, which we'll get to later. We can compose and decompose filters, which means break them down into multiple filters, or you can combine them. So you take multiple filters and you use the transfer function. You can produce a single filter, and you can use it to categorize whether it's a feed forward or a feedback filter. I'll describe what those are later. So getting to some code. Our first filter is very simple. We could just write y equals x, but that's not something we can really build on. we could have a function that just takes the input and returns it. It's also not something that we can really build on. We want to store the past input and output samples because we're going to need to keep those to produce more interesting or complicated filters. So we're going to use a class which allows us to keep the past samples, which we refer to as the filter state. We keep the state and the code together using a class. So this we're going to start with this very basic class, which just contains a process function, and the process function takes a single sample and it produces a single sample. So if we go to the notebook and select in Jupyter Notebook, select the notebook called filters. And again, you need to run the top cell, which will import the libraries and some local functions into this notebook. And once that's done, in my case, it's still running, we can look at what's happening later. So the first thing we're going to do in this notebook is produce this impulse response signal. So the impulse is basically a single sample that's 1 followed by lots of zeros. So if we run that, we get single sample 1 followed by lots of zeros. And we use that basically, we poke the filter and see what it does. It's very, very simple mechanism. So if I do that to the filter from the paper that I've already got loaded, we get this. It's a little decaying wave. So this is what happened when we put that signal above into our filter from the paper, and it produced that result. And a little bit further down, we have the filter that was on the slide. It's the filter that does nothing. So I need to run that so that we can use it. And then you instantiate it and store it in this variable called FLTR, and then run a function. It's a library function that's come with the repository called analyse filter. And when we run analyse filter, we're going to get the impulse response and we're going to get the frequency response. Now our filter did nothing, so we see the same as we saw at the top of the page, just the impulse signal comes straight through. And also the frequency response. The frequency response, it shows frequency on the x-axis, and it's, in the case of this plot, it's between 0 and pi. So pi being the Nyquist frequency, 0 being the DC frequency, and we see magnitude in decibels. So it's most of the filters that we're going to be looking at to start with. You're going to see the plot going down from here to cut. So that was our first filter. It's this filter class here. Now returning to our sequence, our second filter is only slightly more complicated. We've introduced one of the building blocks, which is the delay. So now we have the difference equation. It's showing x of n minus 1 instead of just x of n. So we're taking x of n, storing it for one sample, and then returning it at the output, y of n, and the block diagram, we take the input, we put it through this z to the minus 1. Z to the minus 1 is just a delay of one sample. So it's just a block that you can think about basically taking the input, holding it for one sample, and then outputting it later. And how we get the transfer function, now it's only a little bit more complicated. So we're using this z to the minus 1 again, but in the transfer function, we again have y of z, which is our input, x of z, which is y of z is our output, x of z is our input. And then we multiply this z function by our x of z, and that causes it to be delayed in the transfer function view of things. So one way of getting the transfer function from the difference equation is just to look in this table and substitute. So wherever you see y of n, you put y of z, and wherever you see x of n minus 1, you just have x, z, z to the minus 1, minus 2, and continue that way. And again, remembering that it's a fraction here. So we've taken our x of z, multiplied it by z to the minus 1. And when we do take this fraction, we divide y of z by x of z, which is h of z. We're left with just z to the minus 1. So that's our transfer function. And looking at the transfer function and looking at the block diagram, you see there's a nice similarity. Transfer function is just this. So our code gets only a little bit more complicated. We're going to want to store in a state. So we have an init function, which we're going to define a state value, and we're going to set that to 0. And when we get to process our first input sample, we return the state value, and then we store the input value, and we have to do it that way around because otherwise you overwrite the state before you can return it. It's just something that I get wrong sometimes and wonder why my filter isn't working. So if you modify the filter to look like this, you could print on your filter, you would see this 1, it would return 0 on this line, and then it would return 1 the next time you call the process function. So again, this is all in the solutions file. So this one is filters 2. So we can take that and drop it into our notebook. And when we run the analysis function, we see one thing that we expected, which is the input impulse is delayed by 1 sample. It's just shifted over by 1. And then we see a lot of nonsense in the frequency response. But if you look over the top left-hand corner here, this is a very, very, very small number. This is 1 by 10 to the minus 15. So the maximum of this is 2 by 10 to the minus 15. And what we're seeing is just an artifact of the way that this frequency response plot was produced, which uses an FFT behind the scenes. And there's an awful lot of numerical calculations that happen in an FFT, and you start to see some rounding error. And what we're looking at here is just that rounding error. So we can basically say that this is, again, 0. So our frequency response shows that the frequency basically isn't, or the amplitude at every frequency has not been modified. Only that the signal has been shifted in time by 1 sample. So the first interesting filter that we've got, and it's basically very similar to the one that we built in Reaper, we add the current sample to the previous sample, and that's really it. So again, in the difference equation, we have the output is the current sample and the previous sample added together. And the transfer function, one thing to say here is, because of the linearity principle, you can add these together. So we've actually got the transfer function for the first filter we looked at and the transfer function of the second filter that we looked at. So you could almost just guess this from looking at the 2 filters and just adding these 2 transfer functions together. But if we wanted to do it more formally, you can just use this table again. Swap every y of n for a y of z, x of n for an x of z, and continue like that. But then we can gather, because this x of z appears in 2 places, gather these together into one. Again, produce the fraction y of z over h of z, and it gives us this transfer function 1 plus z to the minus 1. But again, it's easy to think of it more intuitively. If you just look at the block diagram, you can see we have 1 of the input signal, and we have 1 of the delayed input signal, 1 plus z to the minus 1. First thing that we're going to do with it, we're going to use it to find out what the frequency response is. The frequency response is the magnitude of the transfer function. So the transfer function tells us what the magnitude is at a particular frequency, which we again call z. So basically what's happened here, so we've got this is the transfer function. We've multiplied it through by z, still taking the magnitude. And then this just shows that z is -1. But what does it mean for z to be -1? What is a frequency of -1? For now, I'll say that this -1 refers to the Nyquist frequency, but we'll get to exactly why that is a little bit later. If we had found instead that z was +1, that would be the DC frequency. So we have two options at this point. We have the Nyquist or the DC frequency. But if we just go ahead and have a look at that in the analysis, so we've got this filter. All I've actually done here between the last one and this one is add the input value back in. And now we see what we saw before, which is as we get to the Nyquist frequency, you have a sudden drop off in the gain and it's showing -300 on here, but this is basically -infinity. It just can't even calculate it. So it drops all the way to 0 magnitude. And the next thing we're going to do is we're going to introduce a coefficient. So the filter structure is basically the same. We've just added this little B1 here, and B1 allows us to scale the delayed component relative to the input component. And I'm not going to keep going through how to get the transfer function here. Basically, you just add this B1 to the delayed component here. And again, the difference equation, the input plus B1 multiplied by the previous sample. So to create this parameter, we add an extra argument to the init function b1, and we store it in self.b1, and then we multiply it by self.state, which is our state value, which is storing our previous input sample. And when we do that and we analyze it, I need to give it an argument here. I'm just going to give it 1 again. It's actually the same filter that we had before. And we see that this is still happening at the Nyquist frequency. But now if I give it -1, it's at DC. And this is flipped from what we saw with the question of what the frequency was that we were getting from the transfer function. And the output here, we see the output when we've done this is the impulse response is 1 minus 1. So again, we can get this kind of intuition about why this is happening by looking. So what happens if we see the DC signal coming in here? If you remember that the DC signal is just a signal that looks like all ones, or it could be all zeros, or it could be all -1s. It's just some signal that doesn't change. It just stays at the same value forever. And if we take that signal and we take each subsequent pair of samples and multiply 1 by 1 and 1 by -1 in the DC signal. So I multiply this one by 1, multiply this one by -1, and then add them together. I'm adding 1 to -1, so I'm getting 0. It's the same effect that we've seen And as a counterpoint, if I have this impulse response, where our filter is 1, 1. Now, if I have the Nyquist frequency, and I add every pair of samples together, I'm adding this onto this one, I'm adding this one to this one, I'm adding this one to this one. Again, we're seeing that this is going to cancel. The result is going to be 0. And you can kind of see straight away why you get this dip right here, and maybe it's less intuitive why it's going to roll off slowly. But if you kind of look at what happens here, you can kind of believe that it's going to happen slowly, because as we slowly shift these across each other, the effect is smooth and not sudden. But another thing that we'd see here is if you look at the frequency response plot, this is actually not 0 here. This is very slightly higher than 0. And what's happening is, so if we had the signal where we added these two together, so we multiplied whatever it is, -1 and 1 multiplied and added together, we get 2, which means that we've put in a signal and we got out a signal of a different magnitude, where otherwise it shouldn't have changed. So the next thing we're going to want to do is to add another parameter here, which allows us to scale the whole filter's output so that it doesn't have that effect. So we call this normalization. So to normalize our filter, I've just added this extra parameter, b0, self.b0 in the init function, and then we use them again here, self.b0, multiply by the input value now, and I need to add another parameter. So if I previously had to actually run that. I had this filter, it's the same as the one we had before, but now I want to normalize it. So I just make sure that these two added together, that the sum of the impulse response is 1. And now this line is exactly 0. Apologies. Thank you. So we've added these two extra parameters, b0, we've added, which multiplies by our input value. So if I go back a step, so we previously had 1 and an extra parameter 1, so it was the same filter, and we see that the gain is slightly higher than 0, and we normalize it so that the sum of the impulse response is 1 by making these both half. So all I'm doing is scaling the filter that I had before. So again, we can have the same one we had for putting a notch at DC, but scaled 0.5 minus 0.5. So there's our normalized filter. And again, we've just got these two values, B0 and B1. We just scale the input by the same amount that we scale the coefficient that we had before. So a final one before the break. The last one, we just add an extra delay. So we also include the sample before the last sample. And this allows us to produce some more interesting effects than we've had already. So if I show my notebook this time, and then just get this last one. So now we have 3 coefficients. I'm going to set it to 1, 0, and 1. Now you see this notch at halfway. And again, this is what we've seen before. This is the delayed by 2 sample signal. Just as a reminder, on this plot, delayed by 2 samples, so that we see that there's a gap right in the middle rather than at the ends of the spectrum. Again, 2 sample delay. But if I change it to something else, we can see a variety of other effects where it appears in different places. But it's not very convenient to think about what these numbers should be. I can't work out from these numbers what the resulting response is after we've gone past a combination of these 3 coefficients. In this is called a second order filter because it uses the second delayed sample. And that we're going to come to how to analyze that after the break.
Yeah, I guess before we get started, just to talk a little bit about what the process and why we're showing you what we're doing, how we're kind of building up. We find, in terms of developing our products, that lots of our product managers, lots of people are having lots of different ideas, so there are things we want to test out. Hopefully you see the Jupyter Notebook is actually a really useful tool at that point, the process where someone's got an idea and for a product, but we're not sure either whether it's possible or whether it's actually going to be useful, or will work in the way that they intended to, or not. We find using something like Jupyter Notebook really useful for quickly building proof of concept, developing that proof of concept. Hopefully you see being able to kind of plot the signal, look at it, debug bits of it. It's much easier to do in this environment, much more rapidly than building it to a plugin or going the whole way and taking it into one of our pieces of hardware and try and prove it there. It's a really useful way to quickly validate the ideas, to work out whether they're any good. Before we then go further and start thinking about how we interact with that algorithm, how we're going to design the UI and how it's going to hook into the product, or I'm going to talk a little bit later about embedded DSP and how that's different to what we're doing at the moment. So yeah, hopefully you enjoy the next section of the workshop. We're going to move through and get to implementing the actual plugin. Back to Joel.
Okay, so we're going to talk about a bit about complex numbers, which hopefully aren't as complex as the name makes it sound. So the first thing to introduce here is the imaginary unit. So we have this number called I, and it's best not to really think about too much about what I really means. So basically we say that I squared is 1. That's minus 1. I forgot to edit the slide. Anyway, I squared is minus 1. Thank you. And I is not 1. So I is 1, I is not 1. So that, okay, so we say that I to the 0 is 1. I to the 1 is I, and these both come from the basic rules of algebra. So anything to the power of 0 is 1, anything to the power of 1 is itself. And then we've already got that I squared is 1 minus 1. And that when we multiply it again by itself, we get negative I. And then if we multiply it by I again, we get back to where we started at 1. So we kind of have this repeating pattern. If you repeatedly multiply by I, we follow the pattern 1, I, minus 1, minus I, or I to the 0, I to the 1, I to 2, I to the 3. And this is like a clock. We rotate around from the positive x-axis, from 3 o'clock, rotate around counterclockwise. So when we multiply the imaginary unit with a real number, we always get an imaginary value. And when we multiply a real value, an imaginary unit by an imaginary unit, we always get a real number. So we end up basically with real numbers and imaginary numbers together. So in order to represent the fact that we can get real and imaginary values from working with these numbers, we construct this complex number, which is a real number plus an imaginary number. And we can kind of extend the axis. So instead of just having this rotating figure, you also have multiples of I in this vertical direction and multiples of real values in this horizontal direction. And you also fill in all the intermediate steps. So we have a complete plane of values that can take any positive plus any imaginary part. So we separate this into two parts, and we can place anything on the plane like this. And if you wanted to store it, say in C++, you might have a struct like this with a real part and an imaginary part. They're just two separate numbers that we store together. And it allows us, and we kind of plot this as a kind of convenience so that we can just see, visualize where these values appear. But you can also represent any value on the plane as a angle and a magnitude. So we have this magnitude r and angle phi that allows us to place anything anywhere on this plane as well. And one way of representing that, if you remember trigonometry, you have the real part and the imaginary part are, so we have the magnitude, we have the angle, so you have cosine of the real part, so cosine of the angle, sine is the real part, sine of the angle is the imaginary part, and we have a little notation for that, which is this e to the I phi, and we pull out the magnitude as a, so Euler's formula, this is called, gives us a e to the phi, allows us to place anything on the plane with just an angle and a magnitude. If we jump over to the interactive figures, so we've got figures that allow you to play with all of these. So you place a value in the plane. You can see that you change the real part and the imaginary part. We just place that wherever we want. And we get a value. So real part 0.39 plus the imaginary part 0.37. You can add these two together. Here we can play with adding any two imaginary numbers, any two complex numbers. There's a couple of useful things to remember. One here is that if we have things that are at diagonals, I try and align that. I won't try too hard. You have things opposing diagonals here. They would cancel out if the magnitude is the same. Similarly, if you have something where the imaginary parts have the same magnitude and the real part the imaginary parts cancel, so you end up basically with a real value like this. But the magnitude, well, pushes it off to the right. Multiplying two complex values. So when we've got this view of them as an angle and a magnitude, it allows us to think of multiplication as a rotation. So if I take any two values here, we're still placing them just by setting the real and the imaginary part. But you see the behavior is maybe a little bit confusing. So you multiply this point here by essentially the same point, and it ends up over here. But if you think of this as a rotation, so we've got a rotation between the x-axis and this value here, and between the x-axis and the value here, what we're actually doing is we're adding the two angles together, the angle between here and the angle between here, and multiplying the magnitudes. So if instead I put that on the unit circle, so the magnitude is 1, and I do the same for that one, we always end up, if we have 1 and 1, we always end up somewhere on the circle, on the unit circle, with a magnitude of 1. But yeah, you can just play and see the behavior of multiplying these two values together, which, again, it's easiest to think about as this kind of a rotation between the angle between the positive x-axis and the value, and the magnitude of the value. So placing these in this polar view, you can place it anywhere by just setting the magnitude and setting, I've called it phase here, the angle. But again, the angle is between this x-axis and where it appears in the plane. So this allows us to basically set the magnitude and the angle and just see it as a rotation where the angles are added. So if I've got something at so 1 here and 0.5 here, we're going to trace an arc through around this 0.5 point here, because the magnitude 1 and 0.5 multiply together and the angles are just added. And this on the in Euler's formula, you can see basically there's a cosine part. The real part is the cosine part, and the imaginary part is the sine part. So as we rotate around this circle, we're tracing out a cosine if we just look at the real part, and we're tracing out a sine if we just look at the imaginary part. It's a very useful property for us to think about. So it's also possible to use these complex numbers to represent different things. So we might represent a position in the plane as a complex value. So we use it to represent either a phase rotation or possibly a frequency. So when it represents a frequency, and again, there's a interactive figure to look at to do that. So we pick an angle that represents the frequency. So if I just pick a small one here, and it's a fraction of 2 pi, this angle, every sample, we're going to add that angle together, and we rotate around, and we continue to rotate around the circle. So current sample in the next time step rotated around that angle. If I set the angle like so to pi, and remember I was saying that the frequency axis went from 0 to pi. Now this is the view, the same thing from 0 to pi, and what we have here is the 0 frequency on the right hand side, and pi being, that's the Nyquist frequency, and this is where we had that 1 and -1 being the DC, and the Nyquist frequency is the result of where the dip in the frequency was in the frequency response for the filters that we were analyzing in the previous part of the workshop. So where we previously had things flipping between 1 and -1 at the Nyquist frequency, if we think about the frequency of a signal that's in the complex plane, we end up essentially just swapping by rotating this kind of pi radians around the circle. And if we were looking at a real only signal, there we have the Nyquist again. Of course, we've got all the intermediate values, and we can also see the kind of sampling effect. So if I rotate it far enough around, we've normally be rotating in positive frequency in the anti-clockwise direction. If I produce a frequency in the lower half of the unit circle, and I previously called these negative frequencies, yes, we've kind of rotated and continue to rotate this way, but you might also have thought we were rotating clockwise to get from here to here. And it now starts to look like we're rotating clockwise. So this is where this negative frequency idea comes from. So we have this frequency axis that extends positive Nyquist and a negative Nyquist, or positive, the highest frequency we can represent in our sample rate, and negative, the highest frequency that we can represent in our sample rate. And if we had two signals where one is rotating in this positive direction and one is rotating in this negative direction, and we just add them together, we see that they cancel perfectly onto the real line. And this is something that we're going to see in terms of how we analyze filters as we go forward, that we can think of them in terms of essentially a frequency that's rotating this way and a frequency that's rotating this way, or a positive and negative frequency. So let's go and have a look at that. So I'm going to say what we're about to do is the mathematical equivalent of splitting the atom, or actually what we're looking at here is some other particle, so protons here and being collided at the LHC. So this is CERN's CMS experiment. You break the thing and you look inside and see what's happening. And the tool that we're using to do that is these complex numbers. And inside, things are slightly weirder than our intuitions expect in terms of how things work in the real world. But they reveal some way of understanding what's going on. And then you put them back together and try to forget, because it's weird. So again, Z as a frequency, or splitting the atom. You remember a few slides ago I said that Z was a frequency and we'd come back to it later. Well, here we are. So Z is a frequency that's describing a point, or described by a point on the unit circle. So we can find that using that Euler's formula, e to the j omega. That basically is a single parameter omega that's our frequency that specifies a point on that circle. Now, if we follow the procedure that we did before to get this magnitude, so again, I've multiplied through by Z here, and then seen that Z now is minus B. Previously, I just had 1 to minus 1. So now we might want to do that in reverse. So if we say we want a particular omega, so I want a filter that specifies a notch at a particular frequency. I just reverse this. So I say that B is negative Z. So Z, again, it's a point on the circle that specifies a frequency omega, defined as a proportion of the sample rate. And in this filter, what's happening? So if we imagine a complex signal coming in, a complex signal is just rotating around here. It's a complex equivalent of a sine wave. It just rotates. And every sample, we're going to step by a certain amount around here, which is omega radians for the frequency omega. And at time instant x, we have a signal, a sample, and the previous sample was omega radians past. And our coefficient B1 here, it's going to rotate us negative omega this way, so that when we add these two together, they cancel. So let's just think about that again. Our past sample was omega radians behind our current sample. Between our past sample and our current sample, we've rotated omega radians here. And we've also taken our past sample and rotated omega radians that way. So these are guaranteed to be exactly pi radians apart. So that's if we set our input signal equal to the frequency that we wanted to notch out. So we've set up a very specific situation here just to see what's going to happen. And if you had any other input signal coming in, then it wouldn't have this effect. Your past sample would be rotated again by omega, but the difference between these two samples would be something different, and they wouldn't cancel. So that's how you get that smooth curve that affects a particular spot in frequency, and then as you move away from it, you cancel less and less. So at the end of the previous section of the workshop, I was looking at this filter with 3 coefficients. So it's the one described by this block diagram here, and saying I can't work out what filter I'm going to get by just setting these coefficients, except for some very specific, like the 101 example I started with, which I know has got a notch in the middle of the spectrum. If I want to set a particular one, I can't just in my head work out what it's going to be. But we know how to set one notch. But there's a problem. I swap this over here. So if we go back to an earlier filter in our sequence, so filters 4, for example, and start looking at that again. So I have one coefficient, B1, and I'm talking about setting only one coefficient in the filter that I'm describing with a complex frequency. If you take this little section, it talks about complex coefficients. And so we're going to set some complex coefficients. And we're describing a complex filter here, which is one that operates on a value that's rotating in the complex plane rather than a real value. Just going to call that 0 instead of pole. So I put my coefficient I've come up with in here. And I change this, instead of analyze filter, I now want analyze filter complex. And I run that. My problem is, yes, I have a notch exactly where I expected at this pi/4 frequency. That's a quarter of the way through the range of frequencies that we can represent. But my output, it's complex. This is the equivalent of an impulse response in the complex plane. And I don't want that. I want real filters. I want filters that I can use on audio, and this isn't helpful. The way we do that is we move to using a second order filter. And if you remember the effect of one frequency that's rotating clockwise and one frequency that's rotating counterclockwise being added together, so this effect. So I'm going to set up essentially 2 filters, one which is going to be positive frequency and one which is going to be negative frequency. And I'm going to combine them. And we do this like this. So this little over bar, this is called a conjugate. Basically, it takes whatever complex value I had and flips the I. So we flip it from the top half of the plane to the bottom half. So if I had a value, I have this value and I do the conjugate, I get this value. It just flips the sign of the I. So I have one filter. This is the transfer function for the filter that I defined before, which is going to give me a notch at a particular frequency, omega. And I have the one that's got the opposite frequency, or the frequency as if it were rotating the opposite direction. And I didn't say it so far, but the way that you combine 2 filters is you take their transfer functions and you just multiply them together. It's one of the reasons we use transfer functions. It's a very simple operation. So you multiply these together. So we've got z squared multiplied by the omega, z, and our coefficient with the overbar, so the conjugate, multiplied by z plus z multiplied by our coefficient that we've already got, plus that b omega multiplied by b omega over bar. And if you have two complex values which are conjugate to each other, and you multiply them together, the i's cancel. So you end up with this magnitude. It's a property of complex numbers. So we get this just the magnitude of b omega squared. And then we proceed to collecting these together. Again, we've got these two signals. We've got these two coefficients, one with a conjugate imaginary part, and we add them together. Those two cancel. So we actually end up just with a real part. So skipping ahead, we basically end up with three coefficients. 1, 2 times the real part, and that value squared. If we look in the solutions document, this is what it looks like in code. It looks much more friendly to me anyway. B0 is just 1. B1 is 2 by the real part of the coefficient we had before. And B2 is basically the magnitude squared, which is the thing multiplied by its conjugate. So if I go find this is filter 6. That's our second order filter with 3 coefficients. And I create one of those. And I take the 3 coefficients that I've generated here. I change this to 0. 3 coefficients, B0, B1, and B2. So we see the same thing. We've still got a notch here, but we've also got a notch in the negative frequency. And that corresponds to what we were doing. We were adding a filter that puts a notch here to a filter that puts a notch here. But when we look at the imaginary part of this complex impulse response, it's now 0. In fact, all these 3 coefficients are real. So we've got a filter that we can control that's a real filter that outputs notches where we want them. So if I now take away this analyze filter complex, it's complaining that there's some complex values still in here. That could be some very residual part of the calculation here, leaving some complex value in the coefficients. So if you make sure they're definitely real, it's going to be B2. Then we have a filter with 3 coefficients with a notch where we wanted it. So we've put our parts back together again and got something that we were looking for, a real filter. So these locations where we have these dips that we were able to place here on the unit circle, these are called zeros. This is why I renamed the variable zeros. And a zero is a place where you have a dip. And if it's on the unit circle, it's basically takes the magnitude to 0, or it's like negative infinity dB drop. But if you placed it somewhere closer within the unit circle, then you essentially scale that effect so that you're not dropping so far. And if we look at the interactive figures, so you can play with what's happening with these zeros. So we can place a 0 on the unit circle by playing with the coefficients. And if we use some combinations of these coefficients, we get complex zeros. So these would produce a dip at a frequency, which is if you trace around the unit circle. So it's sort of 3/4 pi. And if you look at the frequency response of the feed-forward filter here, so this plot combines the impulse response, this pole plot, sorry, it's a 0 plot, and a frequency response. So as you place these poles, so you can see there's one at Nyquist and corresponding dip in the frequency response at Nyquist and at negative Nyquist. And as we move it around, you see the dip appears at the same angle. So the axis is specified in negative pi to pi. So we've got this dip sort of 3/4 pi, and that 0 appears there in the same location. So we can move these around and just intuitively look at the 0 plot and guess what the frequency response is going to be for that particular filter. And using this plot, we can also see, if we remember right back to the beginning, when we had a delayed signal added to an input with multiple samples delay. So we can see the effect again. As we increase the sample delay, you see all the zeros appearing on the unit circle, and this is equivalent to the plot we had at the top, showing this frequency response. So each of these dips is where a 0 appears, and say in this case we've got a sample offset of 8, and we've got 8 of these gaps between these dips. And if we go down here, again we've got 8 spaces, so it equally divides this circle by 8. Sorry, this is 9, but you get the point. 8 spaces between these dips. And it's always, as we increase this, an equal division of the plane. And the way that this makes sense in this view is if we multiply, say we have this angle and we keep multiplying it, we've divided it into 9. So when we rotate here 9 times, we get back to -1, and -1 was the result that we were looking for. Some slides back. So moving on, we're going to look at feedback filters. So what we're changing now is, instead of looking at the past input samples only, we're going to be looking at past output samples only, just for the moment. So this is actually the first block diagram I showed you. We have something coming in, and then we delay the output and add it back to the input. And we see what's going to happen. You see there's a negative sign here. This is here basically to make sure that when we look at the transfer function, it's symmetrical, so that we have 1 plus z here as well as 1 plus z at the top. If you didn't have a minus sign here, it kind of all shakes out from the mathematics. It just makes the top and the bottom exactly the same. So if we now go back to the filters notebook. And what we want is filter 7. So this is our feedback filter, our first feedback filter. And I'm just going to create a new cell. It has no arguments. And we want to analyze it. So this feedback filter, we've just taken our input value and subtracted the output value. And remember the impulse response. So we're basically adding a sample, single sample 1 at the beginning of time and seeing what happens. And what happens is we keep alternating positive, negative, positive, negative, positive, negative. And we've seen this signal before. This is the Nyquist signal, or the highest frequency that we can represent. So what this is doing, one way of thinking about it, is it's oscillating at the Nyquist frequency. And we see this also in the frequency response. It's very low, and then suddenly it's gone through the roof. Very, very strong resonance at the highest possible frequency on the frequency response. And it's not a very useful filter, but it's very useful for understanding that feedback filters can oscillate. So the next filter hopefully starts to be slightly more useful. We add a coefficient here so that we can scale that feedback path. So if we just add that coefficient, a very small addition, we're just going to add A1 just like we did before. And multiply it by the feedback path and see what happens. So let's give it some value, 0.5 for that coefficient. So now we see, instead of just oscillating like that forever, it's actually decaying, which starts to make it much more useful. And you see we've got, instead of a huge spike at the highest frequency, we've got this little rise to reach it. But this is still a filter which can only affect frequencies approaching the Nyquist frequency. So it's already useful, but we might want to make it more useful. If we flip this, so I changed the sign, instead of being from +1, which was oscillating at the Nyquist frequency, I can change it to -1. This is a mirror image of what was happening with the feed-forward filters. With the feed-forward filters, we were setting it to 1, and it was producing a notch at DC, which was cancelling everything, and set it to -1, it's producing a notch at Nyquist, and it's cancelling. And now, I think it's the reverse. Anyway, now we have the mirror image of that effect, where we're oscillating at DC when we set this to -1. And maybe it doesn't make sense to think of something oscillating at no frequency, but if we just don't make a special case for the DC frequency and just still think about it oscillating here, we can say it's oscillating at DC when we set this to -1. Makes our life slightly simpler. And to think about what's happening. So if we jump into a complex view of this again, we can follow the same logic that we did before. There you were seeing the magnitude, you were just looking at the magnitude of this transfer function. And if we follow that through, we get this 1 divided by And this looks very much like what we had before, where previously we were just saying that if we set Z to negative and it was B1 because it was the feed-forward coefficient, we get a knot where we want it. And now we get a resonance where we want it at the frequency Z. And the reason for that is as this transfer function gets very close to zero, as this, the denominator of this transfer function gets very close to zero, this fraction is going to get incredibly big. So we can see that the magnitude here is going to blow up if it ever reaches zero. So we basically say we don't ever want to actually put we call this a pole. This is where we place this on the unit circle. If we place it on the unit circle, it's basically saying if we ever have that frequency, we're going to blow up to infinity, which is really not good. It's very loud. So yeah, we get exactly what we had before, which is that we set the coefficient to the negative of the frequency that we're looking for, but in the complex plane. So we're looking again at how that filter actually operates, a little bit like in the real domain where we were just bouncing around. So we say the last output is the new input but multiplied by -1, for example, and then we just jump like this. In the complex plane, what's happening? So we got our previous output, which is somewhere in the complex plane, and we rotate it by multiplying it by our coefficient A1. Remember, complex multiplication is just a rotation and a scaling. So our output is rotated by this coefficient between the previous output and this coefficient multiplied value. And then we add that to the input. And together, they produce some value, which is our output. So if we had no input and we just kind of triggered it, as we saw with the impulse response that we were getting, you would just see this just rotating around endlessly. Or possibly if it's less than 1, it would just decay and rotate around until it reaches 0. But if we've got some input signal and it happens to match that frequency of rotation that our state is rotating around, then we start to increase our gain. As you see here, we've ended up outside the unit circle. But if our input signal doesn't match that rotation, then we don't see that effect. So this is like essentially like feedback when you put your microphone close to the speaker and you start getting this feeding back effect because of the constructive interference. The wave adds onto itself and onto itself and onto itself as it keeps going around. This is very much the same effect, but we're just seeing something that's rotating around here for our input and our output. So we can actually look at that. If we find our complex coefficient, and this time I'm calling it a pole and not a 0, and I want it at this frequency, and I change again to filter, analyze filter complex, and I put the pole in here. You see that it's rotating. The impulse at the beginning was 1 and the magnitude is 1. So we do have a filter that's on the unit circle, but because it's got no input, it's not going to blow up. It's just going to keep rotating around here. If we had any kind of input, this would just keep growing endlessly. And we see that it's given us a resonance at the frequency that we asked for, this pi/4 frequency. What we might want to do, though, is to change the gain of this filter. So if I change it to something like that, then we see it decaying until it's 0, and this gives us a slightly smoother resonance. So as we play with the gain, we're able to change the level of the effect. So if it's 0, basically you have a filter that is transparent and just outputs whatever comes in, and as we just increase the gain slightly, we start seeing a smaller bump around the boost frequency that we've asked for. And we can use the same technique that we used before. I won't go back through the mathematics again, but if we took those three equations, say A0, A1, A2, and now these values, but done on the pole, and I find that I'm jumping ahead. Okay. What I actually want to say is, if we go back to the paper, we've been away from the paper for a while, so it's finally time to get back and think about this paper that was the title of the workshop. So, if you look at the very beginning of the paper, there's this equation 1. And equation 1 says that our next sample is some complex coefficient multiplied by our past output sample. And they've defined nicely that our next sample is this. So our coefficient is this, which we've already seen. It's a point on the unit circle by Euler's formula. And if we look at the difference equation that we've just been working with, so we had our input sample and our coefficient and our past output sample. So one thing to say about this is this equation doesn't describe a filter. It describes an oscillator. It's just going to rotate around the unit circle at the frequency that's described by this little value here. And it works by basically rotating by that angle every time step, every sample. It just keeps rotating around. But if we look at our filter equation, if we think about it as basically xn, when we take the impulse response, it's just going to be 1 for the first moment in time, and then thereafter it's always going to be 0. So this is basically setting up our initial condition. So we can essentially tell xn to go away. So now we have an equation that looks like this. And if we kind of think about this Z1 coefficient, basically A1 could be negative. So we can drop the negative sign. And now we basically have the same thing. This yn is some coefficient multiplied by yn minus 1. So we're just going to be kind of rotating around here. And it turns out we've already seen this. This is what's happening here. So the setup to the paper describes a filter that we've already seen. It's this complex filter that's rotating around. But in the paper, they take a slightly different approach to getting real results out. In the paper, they essentially do this calculation by pulling it out using Euler's formula, and then look at only one part. They just look at either the real or the imaginary part. And because that traces out a sine wave, you remember some slides ago, we had this figure. If you look at either the real or the imaginary part of this, we're going to get a sine wave or we're going to get a cosine wave, which are the same thing, just shifted over slightly. So if we get to the way that the paper implements the filter, so this may get a little bit complicated, but don't worry too much about it. It's just kind of detail of how we get these equations from the one that we've started with. So I'm just going to say that y is a complex value, and I'm just going to call y a complex value with a real part and an imaginary part I'm calling c. I was already taken. And our coefficient, well, it's the real part of our coefficient and the imaginary part of our coefficient. So if I take this equation and I just substitute that in here, and I substitute that in here, giving us this. So I've formed the equation slightly differently so that we've got our real and our imaginary parts separated out rather than being kept in a single value, single complex value that we don't know what it is. And then we just do this multiplication. We take the real part, multiply it by the real part of our coefficient, multiply it by this r n minus 1, which we separated out from y. And that's our first term. And we continue real part of our coefficient multiplied by the cn minus 1, which we pulled out from y. And that's the second term. It's complex. So it's imaginary, actually. It's got an I. And we continue this one imaginary part of our coefficient multiplied by the r part of our output. It's the third term and our fourth term. And just remember that when we do this and we get I squared, that's going to be -1. So what we get is 2 real parts and 2 imaginary parts. So we can pull those out actually into 2 different equations, because one relates to this Rn value and one relates to this Cn value. And if we look over here, apart from the input, because we've still got no input to our filter at this point, we have the same structure. It might require a little bit of looking at, but we can see the pattern here. Coefficient multiplied by sample minus coefficient multiplied by sample, and the same on second line. Coefficient multiplied by sample plus coefficient multiplied by sample. So we've recovered the same implementation that they've used in the filter, in the paper, to produce this filter. So this is actually not changed the situation at all compared with this. We've just implemented it by hand, as it were, so that we've got, using Euler's formula, we've pulled it out into the real part and imaginary part. We still have this complex filter, and we still have this same behavior where it will decay, and its normal behavior is just to rotate. And if we just look at if we just happen to look at the real part, we get a decaying oscillation, which actually, if we look at the implementation of the filter from the paper, is the same thing. Just a decaying wave oscillation at a particular frequency. So what we're going to do is actually implement it as it is in the paper. So that's already in the solutions. It's actually a little bit way down. It says the paper filter, and it's called MVM filter. And the MVM is for Max V. Matthews, the name of the co-author of this paper. So again, we have the same structure here. We have a process function, we have an init function that sets some parameters, but we also have a set function. And the set function does all of the calculations that I've been doing to take a frequency, and in this case it says it's a decay time. It has the same effect as the amplitude that I've been setting, and just wraps that all into one function so that we can neatly encapsulate our filter. And then if we take that and I've done that again. Oops. Apologies. So yeah, it's down here in the paper filter, in the solutions. So again, yeah, we have the init function, we have the set function, which encapsulates where we set things, and we have the process function. We take that and put it into the notebook. And again, we just run analyze filter, but I need to give it some different arguments this time. So the arguments we have are the frequency, this TOR value, which is a decay time, and a sample rate. And I'm going to give it a frequency of, say, 1 kilohertz, decay time, something quite small, 0.001, and a sample rate of 8 kilohertz. You can try any combination of values that you like. And we get something that looks remarkably like what we had just using the complex implementation. So there we've implemented the filter from the paper. There's only one small detail. So everything comes from the equations in the paper, which were described in the early slide. So we have the two parameters, x1 and y1, which are, this comes from, here's the calculation of TOR, which was the capacitor charge time value. Then we have an angle, which describes frequency divided by sample rate, which is what we've seen before, but multiplied by 2 pi gives us our phase increment, or the angle that we're going to rotate through each time step. And then we have our two coefficients, which we place. They end up being at 90 degrees to each other around the unit circle. So the one tiny detail here is that in these two, so this is the two equations that I said are the only two that we really need from the paper, that we have this x underscore here, that basically x appears in this line and it also appears in this line. So if we had already set it here, by the time it gets used in the next line, it would be a different value. And that's not actually what we want. So we want to hold it back for a moment and then just set it into the state here. So this is the filter from the paper. But we can carry on. We can have more complex feed-forward filters with multiple coefficients. And so this is one where we have 3 coefficients. It kind of mirrors the one that we saw for the feed-forward filter from before, where we had 3 coefficients. And I was saying a moment ago that if you take that filter with the 3 coefficients, which is in the it's filters 9 in the solutions markdown file. And we take this set of calculations here again. Now we have a real filter. Basically, we've done the same thing that we did before. So just like we had a diagram of poles, a diagram of zeros before, we can also have a diagram of poles, which you just place in the same way. In fact, this is exactly the same diagram. We've just replaced it, the little circles with little x's. But these describe, instead of describing where the where the dip is in the frequency response. This describes where the resonance is. And we can kind of place them again using these three coefficients, but it is much nicer to be able to specify an amplitude and a frequency and do this little bit of calculation and come up with these three coefficients to place it actually where you want. And if we had set a gain here, what's going to happen is these poles are going to come inside the unit circle rather than being on it, which when they're on it is described as an unstable filter. That means that whenever you put any input in, it's going to grow and grow and grow. So you want to set some kind of a gain here. And the magnitude, a different way of looking at the magnitude, apart from just the mathematical manipulation of the frequency of the transfer function, is to think that the distance from a point on the unit circle that you're looking at and where that pole appears. So if I take the example of the zeros here, sometimes they appear inside here. That distance describes the reciprocal of the magnitude. So in the zeros case, if it's on the unit circle, the distance to the unit circle is the magnitude that's going to apply. So in this case, it's 0. And in the case where we have a pole on the unit circle, that's 1 divided by 0, because that distance between the unit circle and that pole is 0, which is a very big number, and that's why we don't put them there. And the final one in the sequence of these filters is where we combine the forward and the backward path, and we get a complete filter. So basically, we're able to place the poles and the zeros on the plot. So instead of having a pole plot and a zero plot separately, we have a complete pole zero plot. I don't have an example here, but you basically place poles and zeros on here to describe a more complex filter, which you combine the feed forward effect, which always cuts from the signal. It always takes gain out at every frequency, and the feedback effect, which always adds gain to the signal at the frequency you've described. And you balance those two together to produce a response that is the one that you want. And this is like a fundamental unit in filters. It's called a biquad, and it's because it's these two quadratics, these two equations of second order feed forward and feedback filters. And this allows us to produce quite a lot of different interesting filters. So if we go back to so we have the implementation of it here. This is the full biquad filter. I'm actually going to jump ahead. If you have a full biquad filter, you can implement any of the filters described in this document. This is a very famous document by Robert Bristow Johnson, which describes how you create all of the different equalizer filters. If you want a notch, if you want a bandpass filter, if you want a shelving filter, you can find them all in this document. Basically, all you need to do is find what he's decided is the three coefficients for each half of this function. Use the same code that we've been using. These calculations are relatively simple. And just plug in the numbers, and you'll have these filters. So after today, hopefully, if you haven't ever done that before, then you'll be able to make all manner of filters just using that code, which is in this notebook here. So I've just taken one, which is the constant Q bandpass filter, and implemented it. So if I do the same thing again, to take that implementation, and it has some parameters again, which are a frequency called omega and a Q value. So I'm going to create it. I'm going to give it a frequency and a Q. And run analyze filter on it. And you see now we have this little notch. It's a much more interesting filter than the ones we've been looking at. because it's able to combine those different effects to produce a result that we actually wanted. And you can place that in different places by changing that parameter. You can change the resonance there by playing with the Q. Make it sharper. As you increase Q, you get a stronger and stronger resonance effect. I'm not actually sure what this frequency is. Okay. So yeah, there's a whole range of filters that you can play with. And back to the paper again. Just after the description of the filter difference equation, we have the transfer function, and we've seen a few of these. But this is the biquad, and you can match all of these coefficients. So we have the B0, B1, and B2 coefficient that's on the top. Actually, only one of those is set, which is the B2. So B0 and B1 are 0. B2 is this R sine theta. And on the numerator, again, we can match these coefficients, 1, A1, A2, to the values that he's described in the paper. And then what we can do is, if you go to the Jupyter Notebook to select a different notebook, and we go look at the filter comparison notebook. And again, we need to import, so run the top cell, and then just run the cells in turn. So the next cell here, it describes a frequency envelope. So over time, we're going from 3.5 kilohertz down to 0 with this little slope here. So it's quite a fast ramp. Only over a few samples, it rapidly decays. And here is the filter from the paper using the structure that I've been describing, building up. So described by the transfer function. Now, if we use this version of the filter, now this structure is called a direct form filter. And it's like the most simple way of taking the filter's description and turning it into an actual implementable filter. But it's not always the best choice of filter structure to use. So we start with a transfer function, which describes the filter in, if you remember, the linear time invariant model. And one of the things that we're breaking a lot, especially if we do this, is the time invariance. So we're changing things over time. And if we build the filter using this direct form, we're breaking the linear time invariant guarantees. And what happens if we start changing the things over time, changing the parameters over time? We've changed the frequency, but the gain has just done this weird curve, made this little wine glass. And we don't want that. We want it to behave nicely. I mean, this could do all sorts of weird things. This could blow up. This could really misbehave. We're kind of lucky in this case that it's only done that. But the filter from the paper doesn't have this problem. If we run that, so it's picking out the MVM filter implementation. And then changing the parameters with a frequency envelope. Same envelope, same decay time, very different result. So there are actually many, many different ways of implementing filters, different structures, different ways of doing it, and they're not all the same. And this is one of the reasons, it's one of the very clear reasons why you might want to use a different filter structure, is because as you change things over time, you get these different results. You get artifacts in the output, and it's very important, particularly if you were doing embedded development and maybe you've got various constraints, to pick the right kind of filter structure to implement the filter that you're trying to use. And just a little bit about why this is happening. So in our complex view of the world, we've got only that one past output that we're just rotating through. But when we've implemented it in this direct form, using the multiple past samples from the output, and we're changing the parameters over time, those past samples actually refer to the filter in the state that it was in the past after we've changed it. And the gain basically isn't the same because we're essentially not referring to the same filter. So you end up with an output that you didn't expect, whereas we don't have that problem with the filter in the paper. And with that, we have another break. Thank you.
Cool. So we are going to get started. So the last bit of the workshop, the raising finish past 12 for lunch. Yeah, I guess just to talk about, so I talked before about why we were using Jupyter Notebook and how that was advantageous. So presumably we've got to a point where what we developed is something that's useful and we actually want to turn it into a product. So just to talk a little bit about the process in that respect. So typically a lot of our DSP, some of it's in place, but a lot of it goes into our hardware products. And at that point, we're kind of dealing with a resource constraints environment. So some of the things that you'll see coming up are one, how, presumably our product manager is kind of approved the algorithm we developed, how we convert that to C or C++, and to implement our hardware products, also how we check that conversion process has gone well. So we're trying to verify that the Python implementation, what was kind of been approved, we successfully managed to get and implement into the actual product itself. But then also looking at the profiling. So lots of the hardware platforms we're working with are resource constrained. We're talking about kilobytes of memory rather than megabytes, gigabytes you get on the desktop machine. So we're really trying to look at trying to get them working efficiently. So looking at how much of the CPU we're occupying, the real kind of focus for us when we get to this point. And it's also a lot more expensive. So we'd love to be able to do a workshop where we're actually building some DSP on an embedded platform, but then we need development kits, we need debuggers in a way. So that is a much slower debug cycle. So using Jupyter Notebook to use reduced plugins is actually a really great way to do a lot of that development on a desktop machine. We've got access to a lot better tooling and development time much faster. Really the last thing for us to do is to put it into our hardware and actually get it working with the product. But then there's also all of the overhead of the kind of UI UX design, so how that's going to work with our control software, how that's going to interact with the front panel, all of those things kind of add up. So the first part of the workshop has been trying to get something building in, prove it's something we actually want to go through that week. And what you'll now see in the workshop is kind of the next stage of extending into an actual product and some of the bits we do along the way. So then hand back to Joe to finish up.
Okay, so just before continuing with the last little bit of the workshop, I just wanted to thank all the people who've been involved with making this presentation work, particularly Edwin, who's in my team at Focusrite, who's done a lot of the work on the plugin and helping with the Jupyter Notebooks, and done a huge amount of work on this. Also, beta testers. We had quite a few people, quite a few colleagues who worked through an iteration of this workshop and gave very, very helpful feedback. And also my colleagues at Sonox for encouragement and advice. And also presenting here today, we've got Ross and James, who are here to answer your questions. So let's continue on from there. Actually, before I get into that, I had a question about how to kind of go back and look at stuff that I've been talking about, things like learning about some of this stuff. And if you look in the repo, there's a file called resources, which includes the paper from today, but also a lot of other helpful information. In particular, I recommend this book, which is a really wonderful introduction to audio DSP. It's not new, but everything in there is very clearly explained. Definitely recommend that one. Julia Smith has all of these many pages which are completely invaluable, actually. And then on the mathematics, there's a lot of interesting things that you can look at, really starting from just complex numbers all the way up to very interesting topics described in the 3 Blue 1 Brown videos, which some of you might be familiar with, which are really wonderful. Yeah, just take a look at the resources and yeah, dive in, have fun. Okay, so back to the getting to the C++ plugin from our Python notebooks. So we've produced something, we've got a filter or some processor that we want to bring into being a C++ implementation. So what we're going to do, we're going to make the implementation, but then we're going to put it through some tests. So we want to do conformance tests, which are going to take us, take our implementation and verify that it's actually correct, that it's doing what we want it to do. And then we've got some performance tests, which are going to check, are they, is the code actually behaving at the speed we need it to? Does it take too many cycles? Does it take too much memory? All these sorts of things we want to test. And we've also got a JUCE plugin, which is like an acceptance testing thing. Does it actually meet our goals in terms of the sound that it produces? The first thing we're going to look at is the C++ implementation. So we're going to start with a class, again, just matching the one that we've got from Python. So just to jump here. So in the repo, there's a source directory. I just go back up here. There's a source directory called source, and it contains the filter itself. This is the class that we're going to implement. So in whatever editor you like, actually, you open this, and we're going to actually fill this in. So again, we have a constructor for this class, which takes some parameters. We have a process function, which takes our samples and returns our processed samples. And we have a set function, which is going to allow us to set our frequency and our decay time. So we're going to want to fill this in. Basically, in the if we have our Python implementation of this, that's also in the repo. So we don't want to take this and turn it into C++. Actually, there's not very much to do. We just need to replace all of these with C++ constructs and replace where we've got these maths functions. We need to replace them with the C++ equivalent in the standard library. And that's actually in the implementation of the filter class at the very bottom of the solutions. So we've got our process function, we've got our set function, and if we were to compare the Python and the C++, it's almost line for line the same. Is double precision really needed? No. One of the reasons might be just when we're comparing with the Python and the C++, we want it to be the same precision, and in this case, no. It depends on the context. Sometimes you do need double precision, but in this case, if you change that to float, it may well work. So if we just take this and find our filter function in the source directory, we can just replace the implementation here and continue to follow instructions which are in the repo. So the first thing we're going to want to do is our conformance tests. So the conformance tests, essentially they run the Python version and they run the C++ version alongside each other, and then using NumPy and matplotlib, but without using Jupyter Notebook, they produce a difference between those two things, and they take the mean power of the difference between those two, which basically tells us what's the power of the error, what's the power of the difference between those two signals. So we're going to want to run that test and see what happens. I've just put the implementation in, and I'm going to give it a go, see what happens. So if you take the line from the instructions, section 3, and then run the tests. Showing the thing, okay. Thank you. To run these tests, so I've built it using the line from the instructions. And another thing that I'm going to want to do is initialize my virtual environment if I'm not in the same shell that I was in before. So let's just activate my virtual environment. And run the tests. And similar to what we saw with the impulse response of something with a very small error, again, we see here 1 by 10 to the minus 8 on the axis. So actually, despite being somewhat scary looking, all this noise, that's actually incredibly small. So we can say that this test has passed. We've got the same output from the C++ implementation as the Python implementation. So we've passed our conformance test, and actually the script has said test pass and given us a power of the error. So we can move on to our profiling. So if we just follow this same instructions again and build the profiling program. So the profiling program, it's going to run the filter and run a dummy version of the filter. So in the case here, it's running a stud sign function and comparing the number of cycles or the amount of time that's passed for running that the same number of times and seeing how we're doing. Now, for me, this is actually a bad sign. On my Mac, it's showing that actually my filter is much slower than my sine function. Running this on other platforms like Windows, it's flipped over so that the filter is actually more efficient. And this is really useful information if you're trying to work for a particular platform that you might actually be wasting your time trying to optimize something until you profile that you don't know whether you're fast or not, even if you're fairly confident that your thing is very efficient. The implementation, the default implementation might be even more efficient and might speculate that it's optimized to an instruction on the Mac or some very optimized code that makes this a really low number that's quite hard to beat. So now that we've done the profiling, we want to move on to the plugin. So to open the plugin project, so we're going to be using Producer. If you've never used Producer before, it's going to ask you to set some things up. Just open it. So if you haven't opened it before, it might ask you to set up the global paths. You'll get a dialog that looks like this, and you need to set these paths, path to JUCE and path to the JUCE modules, to wherever you've got your JUCE located. in my case, I've just got it in the downloads folder because that's where I've left it. And once you've done that, you can go on to using Producer. I'm going to open a project, which is the correct one. And it'll allow you to generate a project for whatever environment matches your platform. So here it says I can generate it for Visual Studio or Mac OS Xcode. I'm going to generate it for Xcode. So I'm on a Mac. And it's opened this project, which I already had open. So now I've got my plugin. It's in this directory. So there's two components to the plugin. There's a editor component and a processor component. And in the case of this one, the editor is going to show you a little keyboard and one single slider, and the processor, it's got a single instance of the filter in it, which when you click on one of the notes on the keyboard, it's going to trigger a single impulse, which is going to trigger the filter to make a sound. And well, let's see what happens. So I'm going to build it so in my environment, I can choose a VST, an audio unit, or a standalone plugin. If I just choose to build it as a audio unit for now, so I'm going to build that. And I suggest, although you can run it as a standalone plugin, opening it in Reaper is much safer, especially if you start modifying the plugin. So here's the one I've just built. I'm going to open that, and it's going to make some sound. Let's make it slightly less loud. And we can make it longer. And it's a plugin. It's not very exciting at the moment, but you can take this filter and you can do all sorts of far more interesting things with it. There's a few examples of what's possible in the repo. So there's different branches here to check out. One's called Advanced Plugin 1, Advanced Plugin 2, and Advanced Plugin 3. If you skip to Advanced Plugin 3, and again, I'm going to build it as an audio unit. I shall need to quit Reaper. And it's built. So now we have this, which we've seen before, which has many, many sliders that represent the gain and the decay time of the various filters. So in this particular one, we've got a bank of many of these filters, and we can make some slightly more interesting sounds and play with harmonics. But you could use this to filter some incoming audio. You could filter it, use it to make some kind of modeling plugin or effects, like, for example, a plucked string or a room mode simulation. If you wanted to have some particular resonances in a room, you could use these filters to do that. There's many, many possibilities. And particularly because we can modulate these filters as much as we like, you can do FM synthesis with a filter, which is an interesting possibility. So that's the possibilities of the plugin. Basically, that's the workshop. So I just want to open for any questions.